The observation of the PK and PD data in DATEXPLORE can bring many insights to choose an appropriate model. Today, I will show you what we can deduce from plotting the PD versus the PK data. In DATEXPLORE, when two types of measurements are recorded and distinguished via the observation ID column, they appear as choices of what to plot on the x-axis and on the y-axis. In this example, I can see the PK over time with dense measurement following a single extravascular administration. I can also have a look at the PD over time, which is also densely measured. PD can be any type of effect or biomarker, for instance. I can also choose to plot the PD versus the PK. If the PK and the PD have been measured at the same time, this is straightforward. If they have been measured at different times, DATEXPLORE performs a linear interpolation. The red arrow indicates how time is passing by. If we have many individuals and the plot is too crowded, I can go to Stratify, Selection, and click on the plus to just visualize one or a few individuals. To understand the different shapes that we can observe in this plot and how to interpret them, I will show you simulations of different situations with MLExplore. These are the different PD models that we will consider. So we have first direct effect models, where the drug concentration directly influences the response, either via a positive effect or a negative effect. We can have models with an effect compartment, where the concentration in the effect compartment drives the response, also either positive or negative. And finally, 4 different types of turnover models. In turnover models, the response can be considered as being produced and degraded, and the concentration can either inhibit or stimulate the production or the degradation. In this MLExplore script, I have implemented the different models I have presented on the slides, and in the graphic tab, I have decided to plot the concentration over time, the PD over time, and the PD versus the PK. In the PD versus PK, I'm starting here at a baseline PD value of 100 and an initial concentration of 0. As time is passing by, I will increase the PK and increase the PD, so I'm increasing on both axes X and Y. So actually I'm going up here. When I reach this point, I'm actually at the peak value for the PK and the PD, and then I go down again in the PK and in the PD, back to the initial value. And you can see that on the way back, I'm using the same path as on the way up. If I'm looking at the IMAX model, actually it's the same kind of plot, just flipped over, because in this case, the response is decreasing when the concentration is increasing. But here again, we see that on the way down and on the way up, the two curves are on top of each other. And this is a characteristic feature of direct effect models. Below in purple, I'm considering the case where it is a concentration in the effect compartment that drives the response. Because the transfer of the drug from the central to the effect compartment is not instantaneous, this induces a delay between the PK and the PD. And we can see this delay if we look at the maximal value, that here is pretty early, but later here in the PD. Because when we look at data, we have a finite number of sampling times, it is not always easy to see this delay between the PK and the PD when we plot PK and PD over time. On the opposite, it's actually pretty easy usually to see something in the PD versus PK plot. And what I see is a loop that is due to the hysteresis. Actually, I can use the animation button to see how the loop is rotating as time is passing by. And it looks like this. So I can see that the direction of the rotation can be clockwise or anti-clockwise depending if the PD is going up or down in presence of the drug. So that was the case with an effect compartment. Here we can see what happens if we have an indirect turnover model, and the situation is again the same with a hysteresis when we plot the PD versus the PK. So the key message is, if I see a loop in the PD versus PK plot, it indicates a delay between the PK and the PD. Let's go back to DATEXplorer. If I browse through the individuals, it's pretty obvious that I have a loop, so a hysteresis. So this means that I will need to use a model with delay. The delay can be via an effect compartment or a turnover model. I will have to try out or choose based on my biological knowledge of the mechanism of action. Let's now check a second example. In the second example, it looks like there is no hysteresis. It's a bit crowded, so let's check a few individuals. I can see no clear pattern. It's pretty noisy, but it looks like the paths up and down are on top of each other actually. So for this data set, I would try a direct response model as a first trial. For the moment, I have always considered that the PD is delayed compared to the PK. In very rare cases, the PD can be in advance of the measured PK. Typically, this is an artifact of the sampling site. For instance, when sampling a venous site while the arterial concentration drives the effect, as it has been seen for nicotine, for instance. In this case, the rotation is in the opposite direction, and this phenomenon is called proteresis, meaning which comes earlier. This is it about the PD versus PK plot and hysteresis. Have a nice week!